Hello everyone. In this video I'm going to go over the practice test 2 solutions. So just a few things about the practice test and the test. All of the test questions will be similar to the ones on this practice test. You will be allowed to use a calculator if you want, but you don't need to simplify your answers. You should show all of your steps and your work. That's so that I can give you as much partial credit as possible. And then I'm going to provide this information bank shown right here. I'm just going to copy and paste it. So we have a table of counting techniques, when to use which technique, so when order matters or doesn't matter, and when you're doing without replacement or with replacement. Then we have the fundamental principle of counting, which says that you can just multiply together the number of outcomes for a bunch of decisions. Selection problem notations, P of NR and C of NR. Basic probability formula, number of ways to do your event on the top, number of total possible outcomes on the bottom. Meaning of the words mutually exclusive and independent, in case you forget. How to check for independence mathematically. Any of these three equations you can check to see if it's true or not. Expected value formula. And then we have the formulas for the compound events, not or and, as well as or when the events are mutually exclusive and when the events are independent. So like I said, all of the test questions will be similar to these, and there will be these are the different types of questions that might appear. We'll have 20 to 25 questions in total. All right, so now let's get into the practice questions. So the first section is using the 26 lowercase letters, the 26 uppercase letters, and the 10 digits 0 to 9, a 6-character password is to be chosen. So we are going to choose 6 characters from this set of characters. So the first question is, how many possible passwords are there that begin with 3 numbers? So the first thing I would do here is lay out a little template of 6 numbers that I'm going to multiply together. So I'm using the fundamental principle of counting here. I'm just going to multiply together the number of outcomes for each of 6 decisions. And the 6 decisions are how many ways to get the first character, how many ways to get the second character, how many ways to get the third character, and so on. All right, so that is the idea for how I'm going to solve this one. So the number of ways to get char 1, number of ways to get char 2, and so on. Okay, so here I just typed out all of those. So this is the basic approach that I'm going to take to all of these problems in this section. All right, so for this particular problem, let's see, what should these numbers be? So the first 3 characters need to be numbers, and there are 10 digits that we're allowed to work with. So for my first character in the password, I have 10 options because it has to be a number. And for my second character, now it doesn't say that we're not allowed to repeat. So if it's not forbidden, then it's allowed, okay? So for the next one, I'm again going to have 10 digits to pick from. And then for the next one, again, I have 10 digits to pick from. Now for the last 3 characters, we have no restrictions. So we assume we can pick anything for these. So the total number of characters are 26 lowercase, 26 uppercase, so that's 52 total letters, and then 10 digits, so that is 62 total characters. So these last 3 numbers here are going to be 62, 62, 62. All right. And then if you want to, you can abbreviate it like this, 10 cubed, 62 cubed. That's also fine. All right, so for the next question, what is the probability that a randomly chosen password begins with 3 numbers? So for this one, we need to do a probability. And we're being asked for the probability of the event that was described in number 1. So we already know what the numerator should be because that's the answer to number 1. Okay, so here we're going to do a fraction where we have answer to number 1 on the top. Right, and then on the bottom, we want to put number of ways to get any password because we're looking at randomly choosing a password and we're going to be randomly choosing it from any possible password. So on the bottom, we need any possible password, the number of any possible password. Okay, so on the top, we're going to have this 10 cubed, 62 cubed number. And then on the bottom, I'm going to lay out another little 6-character template. And I just want to look at how many possibilities are there for each character in the password. So if we're doing any password, then we can do any character. So 62 choices for the first character. And again, we are not told that we can't repeat. So if it's not forbidden, then it's allowed. So we are going to assume we can repeat. And that gives us all 62 characters again to choose from. And then, so for every character here, we have 62 options. Okay. If you want to simplify this, you could write it like this. So 10 cubed, 62 cubed, over 60. Oops, it became 63 mysteriously, sorry. To the 6. You could simplify it further. I think I'll probably just leave it there. So no need to simplify things on the actual test. All right, so number 3, what is the probability that a randomly chosen password does not begin with 3 numbers? So here it says does not, so I am going to use the not formula. Okay, so use the not formula, which says that the probability an event does not happen is 1 minus the probability that it does happen. Okay, so, oops. So that tells me probability that the password does not begin with 3 numbers is 1 minus the probability that it does begin with 3 numbers. Okay, so I'm just going to be doing 1 minus the answer to number 2, right? Because that's what we calculated in number 2. So I'm doing 1 minus that. So the answer here is 1 minus this thingy. Just going to paste it right there. Like I said before, you could simplify, but this is fine. Okay. So number 4, how many possible passwords end with 2 letters? So now I'm talking about a different event, just ending with 2 letters. And it's not asking for a probability, it's just to count how many ways this can happen. So I'm going to do another little template here. And let's think about how many possibilities for the first character. So I'm not told what the first character has to be, so I'll assume I can put anything there. So I have all 62 options, and I have all 62 options for every character until I get to the last 2. So for the last 2, they need to be letters. And be careful here because you don't only have 26 letters, you actually have 52 letters because you have upper and lower case that are being considered separately. So we're going to do 52, 52 at the end here because we want to get letters. All right, if you want to abbreviate this, you can write it like this. 62 to the 4th, 52 to the 2. Now the next question, probability that a randomly chosen password ends with 2 letters. So here we're doing a probability, so it's going to be a fraction, and it's the event that we're being asked about is exactly what we just looked at in number 4. So we're going to put the answer to number 4 on the top, and on the bottom we're going to put number of ways to get any password, which conveniently we already calculated that in a previous problem. Okay. So on the top, just gonna paste this here, and on the bottom, I'm gonna go back up here where I had done number of ways to get any password before, and I'll put that there. Maybe I'll simplify it this time. I don't know. It looks kind of strange to me if I don't. So you can cancel 4 of these 62s from the top with 4 of them from the bottom, and then that leaves you 2 52 factors on the top and 2 62 factors on the bottom, like that. Or you can leave it like this. If you're not confident with your simplifying skills, it's probably safer to not try to do it because you might make a mistake. All right, so then number 6 is how many possible passwords begin with 3 numbers and end with 2 letters? So again, it's not asking for a probability, so I don't need a fraction. I'm just going to be counting, counting the number of ways to accomplish this task. So I need the password to begin with 3 numbers and end with 2 letters. So for the first 3 characters here, I'm going to have only 10 options for each one. because I have to make sure that they are numbers. And then for my last two characters, same as what I did on the last couple of questions, I'm going to end with 52, 52 to make sure that those are letters. And then for the fourth character, I'm not restricted on that, so I have all my options, all 62 options. So that is number 6. And we can abbreviate with some exponents if you guys want to. So this will be 62 and then 52 squared. I don't know, it looks a little funny to me. Maybe I should put parentheses like this. 62. Does this look better? I don't know. Okay. Number 7 is, what is the probability that a randomly chosen password begins with 3 numbers and ends with 2 letters? So again, it's asking about this event that was described in number 6 and just make it into a probability. So we're going to do answer to number 6. And we're going to divide that by number of ways to get any password. Okay, so we know how to do both of these from before. So on the top, we put this number. On the bottom, put this number. Okay, and now I can simplify a bit if I want to. So this one is a little bit trickier. So there's 1 factor of 62 in the top, 6 factors of 62 in the bottom. So that's going to leave me with 5 factors on the bottom. And then on the top, I can leave my 10s, leave my 52s, like that. Okay, so last question here is an OR question. So what is the probability that a randomly chosen password begins with 3 numbers or ends with 2 letters? So now we're going to apply the OR formula. And these events, I'm not sure if they're independent or not, but if they're mutually exclusive or not. Regardless of whether you even know whether they're mutually exclusive, you can always use this OR formula. That will always work. If you're being asked to do like more than 2 events, you don't know a way to do it unless they're mutually exclusive. There is a way, we just didn't learn it in this class. But the OR for 2 events that are mutually exclusive is actually equivalent to the regular OR, because when they're mutually exclusive, this last subtracted term here just happens to be 0. So we're safe to use this OR formula right here. But I actually think in this case, the 2 things are not mutually exclusive, right? It's not mutually exclusive to begin with 3 letters and end with to begin with 3 numbers and end with 2 letters. It's possible to do both those in the same password. So for example, like 111 AAA, that would be doing both. So in any case, we need to use the first regular version of the OR formula, which is right here. Okay, so I'm going to paste that one down here. So we're going to use that. And then the particular events that we're doing are begin with 3, I'll just abbreviate it like this, 3 nums, or end with 2 letters. So we're going to add probability of beginning with 3 numbers plus probability of ending with 2 letters. And then we're going to subtract probability that both things happen. So begin with 3 nums and end with 2 letters. Okay, so these are the 3 numbers that we need to put into our formula. Let's go through one by one. So first I need the probability that the password begins with 3 numbers. So that was the answer to number 2. That was the answer to number 2, okay? So answer to number 2. All right, and then the second one is probability that the password ends with 2 letters. And that was the answer to number 5. Okay. And then the probability that both of those happen is what we're going to subtract, so this part. And that was exactly the answer to number 7. Okay, so that's why I put this one at the end, so you can have everything all ready to be plugged in there. All right, and now let me just go and grab those actual numbers. So it was number 2 plus number 5. See, now's when you're like, oh, I wish I hadn't simplified because I could have put them all over the same denominator. and then minus number 7. That's okay. We don't have to simplify this either. We can just leave it like this. All right. So that is number 8. So it's kind of like magnificently beautiful collection of fractions, and you can just leave it like that. All right, moving along to the next section of questions. A certain company has 50 employees with the following properties. So there are departments and there are locations for each employee. So the 2 departments are research and development and marketing and sales. And then our locations are people who work on site and then people who work from home. So we have the individual breakdown here, and then we also have the totals and then the grand total of 50 over in the corner. So our experiment here is going to be selecting one person at random from the company. So just one person. And we need to determine whether the events works on site and is in marketing and sales are independent or not. So when you're checking for independence, there's always 3 ways you can check, and just do whichever one you like best, or pick randomly if you like. Okay, so these are the 3 equations you can check. When you're checking the equation, you calculate both sides separately and just see if they're equal or not. If they are equal, then the events are independent. If they're not equal, then the events are not independent. Okay, so maybe just for the sake of extra review, I'll do like all 3 ways and just show you guys how it comes out. Since I didn't put very many independence questions, and I think some people wanted more practice. All right. So first I'm going to calculate probability of, so what I'm going to call A here is going to be working on site. So works on site. And I'm going to compare that to, so I'll do like, how should I take this? Versus maybe? No, I guess I'll just do them on their own lines. Okay, so that'll be probability of A, and then probability of A given B will be works on site given, so the other event is in marketing and sales. I'll just abbreviate marketing and sales like that. Maybe I should abbreviate it like this. Okay, anyway. So that's checking the first equation right here. P of A equaling P of A given B. Okay, so the probability that the person works on site. So we're randomly picking out of these 50 people in the company, and 30 of them work on site. Okay, so this is 30 out of 50, or 3/5. Now, the given one is where students tend to sort of like get palpitations of how do I do this? Okay, so what you have to imagine is that you are being given the information that the person you've chosen definitely works in marketing and sales. So they have whatever property it is that follows after given. So you've chosen a person and they are in marketing and sales for sure. And now what's the probability that they work on site? So maybe I should put this as a little explanation, like probability that they work on site if you definitely know they're in marketing and sales. I don't know, does this make it better? Okay, so what we want to do is look at number of people in marketing and sales on the bottom. So we're only looking out of those people because we're sure that we got a marketing and sales person. And now I know I've got a marketing and sales person. What's the probability that they're in, that they work on site? Okay, so on the top we want number of people who work on site and are in marketing and sales, because we're still only looking at that marketing and sales group. Okay, so basically like you're doing both events on the top and then you're doing the given event on the bottom. That's one way to think of it. Okay, so people who work on site and are in marketing and sales is 10 people out of the total 26 people who work in marketing and sales. So now the question is, are these two numbers the same number? Let's see, I can simplify this one to 5/13. This is a little bit hard for me to tell. I don't think they're the same, but if you're not sure, just use a calculator and do an approximation. Okay, so let's see. Okay, so this is what the calculator gave me. The first one is exactly 0.6. The second one is about 0.38. So these are not equal, and that means the events are not independent. You can say they're dependent if you want. So that's the way I would do using the first equation. Now, if we want to do it the second way, maybe I'll paste these separately. Hold on. Okay, so I'll just put them all in their own little sections. So that was the first way of checking. Let's do the second way just to give you guys a little bit more practice. So I'm going to check this time whether, so I'm doing P of B, that's a second event. So in marketing and sales, I want to check whether that is the same as P of B given A. So in marketing and sales given, so the first event was works on site. Okay, so this is my P of B and my P of B given A. So the first one, being in marketing and sales, I'm just looking out of the whole company. How many are in marketing and sales? There's 26. Now the second one is a little trickier. So we're going to restrict to only looking at the people who work on site. So if we only look at the people who work on site and just forget that anybody else even exists, now what's the probability that they're in marketing and sales? So it is going to be, if we don't even remember that these other people are over here, like they're just gone. Oops, that was too gone, hold on. If they're just gone, now what's the probability that the person is in marketing and sales? So it's going to be 10 out of 30. All right, so this is going to be 10 out of 30. Maybe I'll just insert a little explanation over here. So number of people in, who work on site. So the given condition. And then on the top, number in marketing and sales who work on site. Okay, so that's 10 out of 30 or 1/3. Hopefully you guys can see without needing a calculator that these are different numbers, because 26 out of 50 is more than half and 1/3 is less than half. So these are definitely not equal. Okay, so we got not equal, not independent. And the last way of checking, so there's no givens in this way, but you do have to use a multiplication. So if your givens throw you for a loop, then you might want to do it this way. So I'm going to check probability that they work in marketing and sales and work on site. And I'm going to compare that to the product of probability they work in marketing and sales times probability that they work on site. And this time, because there's no givens, all these probabilities are just going to be out of 50. Okay, so the first one and then the next two are all going to be out of 50. So for marketing and sales and work on site, I want the number that are both. So that is going to be these people right here, these 10 that do both things. Okay, and then for these two fractions here, the first one is marketing and sales, so I want the marketing and sales total. It's 26. And then the second one is work on site, just by itself, so I want the total for work on site, which is 30. Okay, and now I'm not too sure how these compare, so I'm going to use a calculator and see what these come out to approximately. Okay, so neither of these needed to be rounded. They're exactly 0.2 and 0.312. So as you guys can see, these are not equal, so the two events are not independent. All right, so that was 3 different ways to check. Whichever way you like and makes you feel most comfortable is fine for these problems. You don't need to do more than one. Of course, if you want to check your work, it might not be a bad idea. All right, so number 10 is very similar. The events are works from home and research and development. So I'm just going to randomly pick the first way, I guess. So I'm going to compare probability of the first event with probability of the first event given the second event. I'll just abbreviate research and development as R&D. Okay. So now, for my first event, there's no givens, so it's just going to be one person from the whole 50 in the company. And how many of them work from home? So work from home is 20. Okay, so that's going to be 20 out of 50, 2/5 or 0.4. Now the second one here, works from home given they are in R&D. That means we know the person we're going to pick is in R&D, then just forget that these other people even exist and only look at these people. And now what's the probability that they work from home? So now what's the probability that they work from home, given that they're in R&D, is going to be 4 out of 24. Okay? So let me just undo that deletion first. Okay, 4 out of 24. And just to explain again, like what we're doing here is the number of people in R&D on the bottom, and then on the top, we're still just looking at the R&D people. So we need people in R&D who work from home. Okay. And so I think this comes to, let's see, 1 out of 6, which is not 0.4, but if you're not sure, you could throw that in a calculator, and approximately 0.167 is what you get. So those are not the same numbers. So not equal, not independent. Okay. So the next set of questions is consider the task of selecting a 4-person committee without repetition, where the order of selection does not matter. So here, I said without repetition. Maybe I should have used the word replacement. That might be more familiar with for you guys. The idea of a committee is like the same person can't sit on more than one seat in the committee, because then it wouldn't be a 4-person committee. So you can't pick the same person more than once for the committee. And here we're saying the order of selection does not matter. And we only ever learned one technique for when order doesn't matter, and that is the C notation. So C of n comma r. Just to remind you guys, C of n comma r means number of ways to choose r things from n things in no particular order and without replacement. And here, replacement and repetition mean the same thing. Okay, so we need that information in order to do this problem. And now we are actually working with the same company here, so I'm just going to paste this chart down here. Okay, so here's our beautiful chart again. And the first question is, in how many ways can the committee be chosen if there must be 2 people from each department? Okay, so I'm still choosing a 4-person committee, and I need 2 people from each department. So I'm going to pick 2 from research and development, so 2 out of these 24, and then 2 from marketing and sales, so 2 out of those 26. And be careful here, it's only asking how many ways, it's not asking for probability. Probability is actually the next question. So we don't need a denominator. And we need to do both of these things, both of these choices. So the 2 choices that we need to make are pick 2 from the 24 in R&D, pick 2 from the 26 in marketing and sales. And then the question is like how to combine these. Like, should we subtract them? Should we add them? Should we divide them? Like, what should we do here? So these are 2 decisions, and you are making both of these decisions to form the complete committee. So it's very similar to just like these password ones where you have to pick all 6 characters before you get the whole password. So it's 6 decisions, and you're multiplying together the options for each decision. Down here is the same way. It's 2 decisions. Grab the R&D folks, grab the marketing and sales folks, and you have to complete both of those decisions before you get the whole committee. So you're just going to multiply these together. It's a little application of the fundamental principle of counting right there. All right, so that is the final answer. You don't need to plug it in or multiply it out or anything. We can just leave it like that. Now the next question, number 12. What is the probability that a randomly chosen committee has 2 people from each department? So basically, what's the probability of this thing that we just did in number 11? So that means we're going to use the numerator, the answer to number 11 for the numerator. Okay, and then on the bottom, we're going to put number of ways to get any committee. Okay, because we're randomly choosing the committee, then we need to select out of the number of ways to get any committee. Right, so on the top, we've got these numbers here. I'll just copy paste. Oops. Okay, Microsoft Word. And then on the bottom, number of ways to get any committee. So you're not selecting any particular characteristics. You're just picking out of the whole company, which is 50 people. And then you need 4 of them. So it'll be like this. All right, and we can just leave it like that. Number 13, in how many ways can the committee be chosen if all 4 people must be from the same department? Okay, so this is a little bit tricky. You can't approach it the same way as you do like doing 4 cards of the same suit, for example, because their 2 departments are different sizes. So what you've got to do here is interpret this event like so. So all 4 people from same department means all 4 from R&D, or all 4 from marketing and sales. Okay, so you need an or in here. I just made it like really big and bold so you guys can see that clearly. Oops. Okay, there we go. Right, so there's 2 different ways you can do this. You can have all 4 from R&D, or you can have all 4 from marketing and sales. And these 2 ways are mutually exclusive. In other words, the committee cannot be both. It cannot be both 4 people from R&D and 4 people from marketing and sales because there's only 4 people on the committee. Okay, so you can't do both of those things. So the mutually exclusive part means that we're allowed to use this formula for or, this one right here. Okay, so the probability of doing one thing or another thing when the things are mutually exclusive is this. And so in this case, we're going to do probability of 4 from R&D or 4 from marketing and sales by just adding together the probability of getting 4 from research and development plus the probability of getting 4 from marketing and sales. Okay. So, oh, I'm sorry. I'm actually doing the next question, aren't I? Like I'm doing this next one down here. You know what? I'm not sure that I ever actually taught you guys how to do number 13. I mean, it's actually all you need to do is like add together the number of ways to get 4 from research and development plus the number of ways to get 4 from marketing and sales. But I don't think we ever like officially went over that or had homework on it. So I'm going to say, I think I have to declare number 13 as something that you don't need to practice. And we'll just skip right to, come on, Microsoft. Nope. There we go. And we'll just skip right to 14. So I'll just like strike through this one. Okay. Yeah, sorry about that. I was just assuming that we were doing it with probability because that's the only way that I taught you guys. Okay. So anyway, back to what I was saying. We need the probability that we get 4 people from R&D plus the probability that we get 4 people from marketing and sales. All right, so what is the probability that we get 4 from research and development? So we want to know number of ways to get 4 from the R&D folks over number of ways to get any committee. All right, and then for the marketing and sales probability, very similar, just gonna change this to M and S. Okay. So my 2 little probability fractions here, I'm still choosing without order, so I'm going to use my C notation. And there's 24 people in research and development, so I'm going to do C24-4. There's 26 people in marketing and sales, so I'm going to do C26-4. Are those numbers right? Yes, okay. And then on the bottom of each of these, I'm choosing any committee, so just 4 people from the 50 people in the company. And that is this problem. All right, let's move on to number 15. So 15 says, what is the probability that a randomly chosen committee does not have all 4 people from the same department? So fortunately, this one is quite easy. So it has the word does not. That means we can use this formula. Probability of not having an event is 1 minus the probability that we do have the event. So in this case, we're going to do probability of not all same department, I guess I'll abbreviate it like that, is going to be 1 minus probability that all are from the same department. And that is just 1 minus the answer to number 14. Okay, So we're just going to do 1 minus, and now be a little bit careful here, because if you just write this like that, then you're only going to have the first term with the subtraction on it. So you need to put parentheses around this whole part here that's the answer to number 14. Oops, what happened here? Hold on. Okay, I fixed that. So make sure you put parentheses around the answer to number 14 so it is all getting subtracted. And then we can just leave it unsimplified like this. Okay, so number 16. What is the probability that a randomly chosen committee has all 4 people from the same department or 2 people from each department? So this is asking us to put together the events from number 14 and number 12 with an or between them. So in this case, you want to think about whether those ways are mutually exclusive or not. So is it possible to have all 4 people from the same department and 2 people from each department? No, it is not. Those 2 things are mutually exclusive. So these 2 things are mutually exclusive. We cannot have all 4 same department and 2 from each department in the same 4-person committee. Okay, so that means we can use this formula for or when the events are mutually exclusive. Okay, so now what I'm going to do is I'm going to add probability that all 4 people are from the same department to the probability that 2 are from each department. Okay, so that is going to be the answer to number, 14? Plus the answer to number 15. Nope, not 15. Sorry, 12. Yeah, that was 12. Okay, so I'm going to get this thingy plus this thingy. And that's it. All right. So I'm going to stop the recording here, and then I will do the rest of these problems in another video.